guys, Mr. G here with another video, and this time we're going to be working for the grade 11. We're going to make another video for electrostatic or about electrostatic. Electrostatic is a different, difficult topic and it's quite important. And this is a good question which have a little bit of everything. So we're going to start now, but please before, remember to subscribe for the channel so you can get the notifications, the different worksheets and other things I post on regular basis. Let's go to question, and this was a question 2 from a question paper. I set up this question quite a long time ago, and I tried to put in it everything more or less that could be eventually asked to the learners. The question said two charged spheres A and B are 30 centimeters apart with charges of 3 times 10 to the minus 4 coulomb is negative charge and minus 2 times 10 to the minus 4 coulomb respectively, as shown in the diagram below. And you have the two charges there, both of them are negative, guys. State Coulomb's law in words. They will always ask you for Coulomb's law in words, so the question is quite important. And here is the answer of this very important law. The magnitude of the electrostatic force between 2-point charge is directly proportional to the product of the magnitude of the charges and inversely proportional to the square of the distance between them. It is a very important law which is going to be asked all the time. This law in symbols is going to be written like this. Force is directly proportional to the product of the charges that are interacting with and inversely proportional to the square of the charges. This is not the formula, this is the law in symbols, okay? So that is question 2.1. It's quite simple, guys. Question 2.2, calculate the electrostatic force exerted by charge A on B. So the force on B, and let's quickly go here because it may be needed or it is going to be needed later on. Here, this exert a charge, a force on that direction. That is the force from A on B. Now, why is it pointing in that direction? Because the two of them are positive, are negative, and they are repelling each other. And then, before we even answer that one, we are going to answer quickly question 2.3 right now. Note here, this is the force from A on B. The question 2.3 says how the magnitude of the force exerted by B on A compare with the magnitude of the force calculated in question 1.2. It doesn't matter what question is that. This is question 2.2. It doesn't really matter which one you calculate. B will exert the force on A. They are repelling each other. In this case, is pointing in that direction. This will be the force from B on A, guys. And these two forces are equal in magnitude and opposite in direction. This is Newton's third law. Force A on B will be equal to force B on A, but in opposite direction, and that is why I'm going to add the minus. This one is Newton's third law. I'm going to write it here. It is important to know the forces are equal in magnitude and opposite in direction. They don't speak about direction, but the magnitude must be equal to. Now let's calculate the force, because that answer was it doesn't matter what is the force. This is question 2.2. Now for this one, the force is equal to K, the product of the charges, 1, 2 divided by the distance square. And when you substitute everything here, and the answer here is 6,000 Newton. Now note, this could also be 6 times 10 to the 3 Newton. It's the same answer, guys. It's just scientific notation. And now before we go to the next question, I want you to be clear on something. In this formula here that we are busy with, this formula here, you do not substitute the signs. So do never substitute the sign here in the substitution. Do not, let's write it down. Do not substitute the signs, either positive or negative. If it's positive, it's not a problem, but if it's negative, it will give you, or it will attempt to give you, wrong answer. Now the question here was calculating the force, and force have a direction. So in this case, we are going to say that is away from B. You can write to the right as well, and it won't be a big problem here. So let's write the direction here, and I am going to write to the right. I don't like to write too much. I prefer to say away, but the thing is, you must have direction. That is question 2.2, question 2.3 we already answered, and we go into question 2.4. Define electric field at a point. There is a question that we answered previously in which we said you must go to the formulas to give you that specific answer there. Question 2.4, let's answer it here. Now, but before we answer, I want you to point that this here is the formula you will find at the end of the exam. This formula is given to you, and all you have to do to answer this question is to read that formula. So this one is this statement say that the electric field at a point is force per unit positive charge at that point. That, guys, is the answer for that definition. Is a definition you have to learn, nothing to say. However, it is the formula, guys. If you manage to read the formula, then it's not a problem. So let's go to question 2.5, which is the most difficult question in this test, and is in actual fact a difficult question, by the way. So let's answer question 2.5. Say find the distance from B. They want the distance from B, just B, along the line that passes through the points charges where the net electric field is 0. So for this one, we're going to erase all the forces we have here, because we're going to use this picture quickly to understand this question. Now the question said, find the distance from B. So we are measuring from B along the line that passes through the point charges where the net electric field is 0. So we're looking for a point. We're looking for a point where the net electric field is 0. And we have two options here. We have either on the right side of B, or we have between A and B. So let's place it first between on the right side of B. So if we place that point they want us here, if is there, what is going to happen? Remember those points, and it's the definition, those points, they are always positive. You can see it there, always positive. So this point I placed there, this purple point is a positive point. So what is going to happen? A is going to pull towards itself like this. This will be the electric field due to A, and then B is also going to be pulled towards itself. This is the electric field A. So they cannot be then the electric field, the net electric field at this point cannot be 0, because it will be pointing to the left. However, if I place the point in between the charges anywhere, I'm not going to place it right in the middle, but if I place it somewhere, let's say at that place there, remember, we're still working with that positive point. So what is going to happen here? A is going to pull to the left. This is the electric field due to charge A, but B is also going to be pulling because it's also negative. So that means, guys, that this electric field, or this point, must be most definitely on the left side of B. It must be in between the charges. Now, something I want to point out, and take a note in case you get another question. If they ask you always for this point, and the charges are like charges, either too positive or too negative, like it is the case here, then that point is going to be in between. If it's one positive and one negative, then the point is going to be outside. That is the case. I wanted to take that note because it would be an important note for later on. So we're looking for a point that is in between A and B. We're going to stop there. We're going to carry on, and we'll come back to the picture just now. Now, question 2.5. What we're looking for? First of all, we're looking for the distance. How far from B? But we know at that point, the net electric field, is equal to 0. They tell us that. Okay? And for the net electric field to be 0, and let's explain this one quickly. You can see here from the picture that you have two directions, one to the right and one to the left. That is the situation we have here. Okay, so when you have such situation, guys, you have to select direction. So let's, for instance, say right is positive, and this is completely up to you. This means that right is positive. Therefore, the electric field B is going to be positive and the electric field A is going to be negative. So if you come back here, it's going to be the electric field B minus the electric field at point A is going to be equal to 0. And if you rearrange, you get that the electric field A is equal to electric field B. You don't have to do all this. You can start from here already. You can begin the question from there. It's fine as long as you understand, and be careful with the minus, because some people already here they write EA equal to minus EB, and that is going to lead to a wrong answer. Now, E, or electric field at a point, when the electric field is not uniform, E is equal to K multiplied by the charge divided by the distance square. So we are going to substitute this one for each of the different electric fields there. Then we have that K multiplied by QA divided by the distance A square is equal to K QB divided by the distance B square. And then K is the same, and therefore you can simplify K. So what are we going to have right now? We have that QA divided by distance A square is equal to QB divided by distance B square. But now we have to go to the distance, because there is a tiny issue with the distance, which is, it could be confusing. You only have the distance between A and B. You don't have the distance between the point, because you in actual fact don't know where the point is. But because of that, then we are going to call distance from B to the point, we are going to call it X. So this distance here, from here to here, we are going to call it X, because we don't know it. So X is going to be the distance B. Let's write R. RB is going to be equal to X, because we don't know it. It is pointing on that side. And A, the distance from A to the point, now this is mathematics. Now this distance from here to there is going to be then the 30 minus X. This distance here will be 30 minus X, because it is the distance from A to this specific point. It's simple math. This one is RA, which is equal to 30 minus X. But be careful, because you cannot work with 30 centimeters, so it must be converted to meters. In actual fact, it will be RA equal to 0,3 minus X, and this is the distance A. Important, and this could be one of the very tricky part, which is to determine the distance there. So if we substitute those numbers there, let's write it here. RB is equal to X, RA is equal to 0,3 minus X. And guys, this is what we must substitute in that equation there. So we are going to do all the substitution. And all is left is now to work with this equation here, which is mathematics. So let's do that one real fast. Now we here have a quadratic equation of the form ax squared plus bx minus C equal to 0. This is A, this is mathematics. This is B, and this is C. And then we are going to use the formula x equal to minus B plus minus square root of B square minus 4AC divided by 2A to get the answer here. So that is all we are going to do. We are going to substitute in that formula, which I am going to write in this side here. And when you substitute this one, if you substitute the positive in this formula, you'll get the correct answer, which is equal to 0.135 meters. If you substitute the minus, you will get the negative answer, which is not correct. So where is going to be the sphere? It's going to be 0.135 meters on the left. So it's going to be, that point will be 0.135 on the left. In other words, it will be on that distance there, more or less where it is. So I hope this is understood. This is a difficult question. This is one of the most difficult questions that could be asked to you guys. Now we continue with the next question. We're almost done here. Sphere B is moved and make contact with sphere A. It is then moved back to its original position. So what they did is they moved the spheres. They moved the sphere. This is A, and then this here is B. They make contact, they touch each other, and obvious during the touching, what is going to happen here? Electrons were moving or transfer from one to another. In this case, it moved from A to B. The electron moved from A to B, as you can see there. Because A is more negative, it does in actual fact have more electrons. Okay, so calculate the new charge on each sphere. Now to calculate the new charge in each sphere, you need to use the law of conservation of charge. So this is question 2.6.1. all right, let me see, this is 2.5, yes, 2.6.1. so the new charge on each sphere is equal to the addition of charge A plus charge B divided by 2. This is quite simple. When you substitute here, question 2.6.2, they ask you to calculate the change, how much electrons were transferred during this process, all right, during this touching process. So to do that one, we have to first calculate the change in charge. We need to know how much change or the charge changes. Remember, the number of electrons is equal to the charge divided by the elementary charge. However, we are not working with charge because we don't want to know the number of electrons there are. We want to know how many electrons did move from one charge to the other. So to do that one, guys, the first thing you have to do is to calculate the change in charge either for A or for B. So you have to know how much that charge changes. So, and remember, in physics, any change is going to be final minus initial. So in this case, it will be the final charge A minus the initial charge A. And when you substitute this one, the final is what we just calculated here. So you have the change in charge A is going to be equal to minus 2,5 times 10 to the minus 4 minus the initial charge A was minus 3 times 10 to the minus 4. That was the initial charge. And when you calculate here for A, you will get that there is 0.5 times 10 to the minus 4 coulombs. It means that A will stay with a charge of the change that A have was 0.5 times 10 to the minus 4 coulombs. And therefore, if A loses electron, it will decrease by this one, and A and B will increase by that one. So when we calculate the number of electrons now is electrons, so we are going to use the change in charge, but the negative one. It would be for B. So it will be minus 0.5 5 times 10 to the minus 4 divided by the elementary charge, which is minus 1,6 times 10 to the minus 19. And when you calculate this one, you get that 3,13 times 10 to the 14 electrons were transferred. This question is a tense question, but it's a very good question. That's why I place it in this specific grade 11 question paper. Define electric field and draw the electric field pattern for the two spheres. This is not electric field. This here is electric field at a point, so be careful with that one. All right, so let's go to the definition of electric field and let's go to the draw of the electric field pattern, obvious after they touch now. Electric field is the region in space in which an electric charge will experience an electrostatic force. That is the definition for electric field. And to finish, we have to have the pattern. Now, both charges, as you can see here, each of them will have a charge of negative 2,5 times 10 to the minus 4 coulombs. So we are drawing now the charges. And this one, it seems easy, but people attempt to have a weird drawing. You have two negative charge here. All right. Now, what they're going to happen? They are going to repel. So the electric field lines that you are going to draw are going to be pushing away from each other, and they have the same magnitude. Therefore, you should have the same number of lines. I don't know. I don't recommend to be drawing a lot of lines, but look and note that the lines are always pointing away from each other. So I see very, very funny drawing. The direction is in because the electric field around a negative charge is going in. So this is the direction of the electric field lines. I am worried because the lines here, I seen straight lines like this one here, which is not correct because this line is being pushed by the other charge. So the correct way is to have turn. So for instance, let's say you draw another line here. This line is not straight, but it will be turned towards the other side because they pushing each other. The same if you draw a line, for instance, on this point. All the lines are pushing away from each other, even at the back. If you have a line here, it will be attempt to move a little bit away as it is there, or here, for instance, is away from there. Now, these two charges are the same in magnitude, therefore, you must have more or less the same number of lines. It must be the same number of lines because the electric field is the same. So guys, this is the end of the question. I hope it helped. If you think it helped, then subscribe for the channel, thumb up. You can write comments. I'll see you next time with another question. This is Mr. G, and I'll see you next time. Thank you. Good luck.